So today I wanted to look at the central processing unit. So central processing unit, obviously the thing that does most of the control for the system. So I'm sure you've heard of the idea of an Intel Core i3 or a Core i7 or an AMD processor, etc. So these are the components that are doing most of the work as far as we're concerned. So they are sending electrical signals to other components. They are making the system run, doing the calculations that we need to do. So you could say that sometimes people talk about the central processing unit as being a bit like the brain of the system. However, human brains think, and of course computers don't, although I like to think of it more as a controller which is running a constant stream of instructions. So we've got a number of components involved in the CPU, and at GCSE level, you need to know some of these components and how they fit together. So if we think about the actual looking of the CPU, then we have got a number of components that we can identify. So first of all, this is just the idea of a CPU. So this bit here is the CPU. On this side, we've got RAM. So we've already talked about RAM and about what it does. So it holds instructions and data. So both of them in a von Neumann architecture, which is the sort of architecture we're talking about here. It holds instructions and data. So each location in RAM has an address. So that's going to be an address, a binary address, if you like. I've written them in hex here, but it's going to be an address of where to find whatever it is that's in that location in RAM. And to find that, we need a bus, which is called here the address bus, to hold an address of where we're looking for some information. Now, this is the idea of a bus where it's got a number of parallel lines. So in this case, we've got 8 there, 8 parallel lines. If we had 8 parallel lines, going back to the idea of our binary, we could think about how many addresses we could put in there. And when we did this in our thinking about data representation, we did some of this where we thought about how many numbers we could put in. So with 8 bits, we can have a 128 and a 64 and a 32, etc. So we can do 255 as the biggest number, and we can also have 0. So that's 256 different addresses or different numbers we could put in here. So if I had an 8-bit address bus with 8 wires, I could only access 256 memory locations. Now, in modern computers, most address buses are now 64-bit, which is very large, and you can access a great deal of RAM. When we had 32-bit computers, when the address bus was 32 wires wide, we could access about just over 4 gigabytes of RAM. And after that, we couldn't access any more because there were no addresses for it. So the address bus and the RAM, they've got a direct relationship with each other from that point of view. This bus at the bottom is the data bus, and you can always recognize the two if they're drawn in a picture, because address bus is one way, it just holds addresses and sends them to RAM. Data bus is 2 ways because we might need to read from RAM, and sometimes we might need to write something to it as well. So that's the data bus, and it works in just the same way as the address bus in as much as it has a bunch of wires, parallel wires. So then we've got a few registers. So this register, which is just a single small piece of memory inside the processor, it's the memory address register. It holds the address just before we put it on the address bus. And this one's the memory data register, sometimes called the memory buffer register. And that holds the data immediately after it's been brought back from RAM or immediately before it's sent to it. After the data comes from RAM, it's going to go into this register here. No, it's not going to go into this register here because it's going to go into this register here. And this register is the current instruction register funnily enough, it holds the current instruction that's being worked on. And this register that I almost mistook for it is actually the program counter. PC program counter, this one. It holds the next instruction that we're going to put into the memory address register to find, and it counts up, which is why it's called a program counter. So this box we've got here is the control unit. CU, control unit. Control unit controls the rest of the processor and also does the decoding of the instruction that arrives in the current instruction register. So it decodes that and gives it, splits it into an operation code and an operand, or a bit of data that we can use. The operation code indicates what we're going to do. Could be store, could be add, could be fetch from memory, could be all sorts of things that we could do. That's the control unit. So the other important bit on this side is the ALU, the arithmetic logic unit. ALU, and as the name suggests, it does all of the arithmetic, so adding essentially, and all of the logic, so comparing things for logic. So if we can compare two numbers and decide if they're the same or not, or if one's bigger than another, or if one's smaller than another, etc., it does all of that work, the comparison. So it takes two inputs and it has an output to this thing called the accumulator, which accumulates values. This little bit of memory here is a flag register. So they're literally single bits that we can set to show whether there's been a negative result or a divide by zero error, or various things that can happen in the ALU can be set here as a flag. This external arrow here is the clock. And you might have heard of the clock on a CPU. It's sometimes, something like 2 gigahertz. So all that is a current applied to a crystal. The crystal oscillates and provides a timing signal for the processor. If it's 2 gigahertz, that's 2 billion ticks per second. So the computer, the CPU, can do some form of operation every time there's a tick. So it's a bit like a game of rounders, where if you're at the first post and you've hit the ball, but you didn't get any further than the first post, you have to wait until the bowler bowls before you can run again. And that's the clock that provides this timing signal. And it just looks like a square timing signal, just like this. So it's continuous and constant. So the only other bit on here that I haven't talked about is this bit of blue memory here, which is cache. So cache is very fast memory locations that are on the processor, and we can use cache for storing instructions that we've fetched from RAM that we haven't quite used yet, so we can make an instruction pipeline in that and keep fetching instructions. Or we can use it to store intermediate calculations. So if we've done one calculation in the ALU, we have to store it back here and then do another calculation based on the result. It saves us from fetching it back from RAM, or from storing it and then fetching it back from RAM again. So generally, that's everything to do with the CPU components. So when we come to talk about fetch execute and the fetch decode execute cycle, which is this idea of fetching from RAM, bringing back, decoding, executing, and then doing it again and again, we'll talk about this a little bit more. But this is the basic idea of the CPU and how it interacts with RAM. So on